Welcome back to this finite element analysis session on offline mode. So today in this class we are going to discuss about the implementation of two-dimensional elements. So we are going to see about two-dimensional element. So implementation of two-dimensional elements. So in finite element analysis. So there are two broad categories in which we're going to divide the two-dimensional problems in, as far as finite element analysis is concerned. One is scalar variable problems. And another one is vector variable problems. So what do you mean by scalar variable problems? So here, in case of scalar variable problems, the primary unknown which we are going to find using finite element techniques, it won't vary with respect to the axis involved. Okay. Irrespective of the axis, it will be having only one value of primary unknown. Whereas in case of vector variable problems, as in the name itself, you can say any primary unknown depends upon the direction. Okay, whether it is acting in x direction or y direction. So depending upon the axis of, depending upon the direction of force, or depending upon the direction of any external load, the primary unknown value will vary with respect to the dimensions. Okay. So here we are going to consider the dimensions in case of vector variable problems. In case of scalar variable problems, we are less bothered about the dimensions. So it will be having only one particular value of primary unknown. So here, in both the cases, what we are going to see is, so there are two different kinds of elements we're going to see. One is called CST element. So otherwise we can say it is a constant strain triangle elements. Constant strain triangle elements. So wherein the strain will be constant throughout its cross section. That is what its meaning. So constant strain triangle actually. So it will be a triangle in nature. So if you consider the linear triangle, so it will have only the corner nodes. Assuming this triangle, so which will be having three different corner nodes. Otherwise, we will keep this an LST, linear strain triangle. Constant strain triangle elements, CST. Constant strain triangle elements. Okay. The second one is what we are going to see about this quadrilateral element. Quadrilateral element. So it will be a quadrilateral in nature. So a linear quadrilateral element consists of all corner nodes. It has 4 nodes at each corner. Okay. So as we discussed earlier, so there are 3 important parameters we need in case of finite element analysis. One is called shape function. Shape function. Next one is called strain displacement matrix. In short form, it will be denoted as N, shape function. Strain displacement matrix. And the third one is stress strain matrix. So these are the 3 important parameters we require for deriving the stiffness matrix for any kind of elements. Okay. So ultimately, what we have to do is we have to frame an elemental equation F is equal to K into D. So this is the generic equation of finite element techniques. Whereas we require two different vectors. One is called stiffness matrix and another one is called force matrix. Okay. So based upon these two values, we are going to see about the deflection, unknown deflection value at each node. Okay. So in this offline class, so we are going to derive the shape functions. Okay. So shape function will vary depending upon the elements. Okay. So here we are going to derive the shape function for the CST element. So that is what we will see in this class. So let us put like this. So derivation of shape function for the CST element. So this is what we will see. Derivation of shape function in CST element. Okay, so first of all, let us consider CST element. If you consider the two-dimensional case, so by default, we'll be having two different values. So forget about whether it is belongs to scalar or vector variable problems. But anyway, we will be having two different values, two different. Let us assume a deflection be the values we have to find. So deflection be the primary unknown we are supposed to find. So let us consider this is one, this is two, and this is three. So these are three numbering schemes in which this could be x1 comma y1 in the Cartesian coordinates. This could be x2 comma y2. And for node number 3 could be x3 comma y3. So these are the different Cartesian coordinates in which we're going to place it in the Cartesian coordinate systems. X comma y. Okay. And as far as primary unknown is concerned, so we require actually how many degree of freedom would be there here. So let us assume node number 1, u1 and v1 be the deflection. Let us assume at node number 1, u1 comma v1 be the deflection. Similarly, at node number 2, u2 comma v2 be the deflection, and node number 3, u3 comma v3 be the deflection. So totally, how many degrees of freedom are there? Totally, we will be having 3 into 2, 6 degrees of freedom. So otherwise, we can say, so this deflection, which involves 6 degrees of freedom, u1, if you put it in the matrix form, v1, u2, v2, and again u3, v3. So likewise, you can put, or else you can put like this also. Here you can put u1, u2, u3, and change the order. v1, v2, v3, like this you can put. So you can consider any other form. Okay. And in the step 1, in solving, in deriving the shape function, so what we have to consider, the two, generic form of deflection function. We have to consider the trial function, step 1. Step 1. So to consider the, assume the trial function, assumption of trial function. Assumption of trial function. So as I said, the number of terms in the polynomial equation depends upon the number of degree of freedom. So here we'll be having 6 degree of freedom. So totally the size of this, number of terms in the polynomial function will be 6. So what would be the generic form of polynomial function here? So we can write a0 plus a1x plus a2y plus a3xy plus a4x square plus a5y square plus a6 x square y plus a7 xy square. So likewise it will go plus also. So here, if you consider the x direction, I mean, if you consider the only one direction, okay, totally you will be having three terms. You have to suppose consider for three terms. Similarly, if you consider the v deflection in the y direction, so similar things happen. Okay, so totally you have to consider the 6 degree of freedom and 6 terms here in the polynomial equation. Okay, and if you write this, so you will get totally u is equal to, let us assume, a naught plus a1x plus a2y. So this is one such equation for deflection in x direction. Okay, deflection in x direction. That is what it is u. Similarly, for y direction, it is assumed as v. So we will be having the same three terms. You have to consider the deflection in two different directions. U is nothing but deflection in x direction. V is nothing but deflection in y direction. So u, first of all, finding out the u in x direction, you have to consider first three terms in the polynomial equation. Similarly, for v, again you have to consider three terms in the polynomial equation. So the rest of them can be. So we can put like this. Okay, so this is generic term. Okay, so for another thing, we can consider it as a3 plus a4x plus a5y. Okay. Let's consider this as equation number 1 and this is equation number 2. Okay. So these are the two polynomial equations. So you have to consider while deriving the equations. Now we need to apply step number 2. Okay. So don't forget this. You have to choose depending upon the number of degree of freedom. So here in x direction we'll be having 3 degree of freedom. In y direction again we'll be having 3 degree of freedom. So totally we'll be having 3 in x direction, 3 in y direction. So totally the number of degree of freedom and number of terms here it will be 6. Okay, step number 2 is applying boundary condition. Applying boundary condition. What is boundary condition here? At x is equal to x1 comma y1, I mean sorry, x comma y. If you assume the coordinates x1 comma y1 is the first coordinates at node number 1, what could be the corresponding deflection value, right? So you will get u1 is equal to a0 plus a1 x1 plus a2 y1. Similarly, you will get v1 is equal to a3 plus a4 x1 plus a5 y1. Okay. In a similar fashion, you will get node number 2, x2 comma y2. Look at the equation. u2 is equal to again a0 plus a1 x2 plus a2 y2. Similarly, v2 is equal to v3 plus a4 x2 plus a5 y2. Similarly, for the third node, this is node number 1, this is node number 2, this is node number 3. For third node, we have x3 comma y3. So if you have x3 comma y3, the equation becomes u3 is equal to 8 a naught plus a1 x3 plus a2 into v3. So similarly, v3 is equal to that a3 plus a4 x1, so x3 plus a5 y3. Okay. Again, the next step, what we have to do is we need to find the unknown parameters or the unknown parameters here. So we get unknown parameters as a0, a1, and a2. a0 and a1 and a2. Right. So these are the unknown parameters in case of deflection and at x direction. Similarly, at deflection at y direction, we get the unknown parameters we need to find a3, a4, and a5. So these 6 unknown parameters we are supposed to find. So how to find these 6 unknown parameters? So we'll be having the equations like this. And if you consolidate, if you derive the equations from the simultaneous equation forms, you have a0, a1, a2. You get the value from here, right? So likewise, you get 1, x1, y1. Here we get 1, x2, and y2, 1, x3, and y3. Okay. So this is the generic form you get. So the inverse of, and here we get u1, u2, u3. So how did you get this form? So from this simultaneous equation, I mean, what we have derived is u1 is equal to a0 plus a1 into x1 plus a2 into x2. Similarly, u2 is equal to what? a0 plus a1 into x2 plus a2 into x2. Okay. Similarly, for u3 is equal to what? a0 plus a1 into x3 plus a2 into x3. Right. So if you put it in the matrix form, you'll get. So I will write here. You get u1, u2, and u3 becomes here 1, x1, y1. So here this y1. So this y1, this y2, here this y3. So we get a1 x1 plus a2 y2. So here we will get 1 x2 y2 1 x3 and y3. So multiplied by a0, a1, and a2. Right. So this is the matrix form of this simultaneous equation. Right. So if you want to calculate the unknown parameters, so you need to bring this entire matrix to the left side, and it will become inverse. So our aim is to calculate the inverse of this matrix. Okay. And in turn, if you find the inverse of the matrix, okay, you find the inverse of the matrix, ultimately you get the value of all those unknown parameters. Okay. So let me, in short, we'll write all those known parameters here. Okay. So if you, I think I don't want to repeat the procedure for calculating the inverse of the matrix. I think you might have already know how to solve this problem based on the inverse of the matrix. So I just skip and I will write the values of all those parameters. Okay, A2. Okay. The value will become like this. We'll get actually. So if you calculate, if you want to calculate the triangle, okay, is equal to 1 by 2 of 1 x1 y1 1 x2 y2 1 x3 y3. If you calculate the modulus like this, so it will become the area of the triangle. So from this equation, so we are supposed to we will get one value. When you calculate the inverse of the matrix, you get the value like this, and this value has been considered as area of triangle ultimately, and we can write this actually 1 by 2a. So plus you get 1 by 2a into x2 y3 minus x3 y2. Here we get x3 y1 minus x1 y3. So if you find the matrix, I mean, inverse of the matrix, you will get this value. X3 y1 minus x1 y3. Here you will get x1 y2 minus x2 y1. In the second part, you will get y2 minus y3. Here you will get x3 minus x2 minus x2. Here you will get y3 minus y1. X1 minus x3. Here we will get y1 minus y3. So y1 minus y2 here. Here we will get x2 minus x1. So this is what the value of the among parameters A0, A1. Okay. In short form, what we can do is, instead of this value, we can consider it as a simple term by 2a into this term. You can take it as considered as alpha 1. Here this is alpha 2. This is alpha 3. This is can be considered as beta 1, beta 2. Here this could be gamma 1, gamma 2, and gamma 2. These are the values of common parameters. Okay. So if you substitute these values in the generic equation, otherwise in the matrix, so we are supposed to find, we have to convert it in the generic form of u is equal to n1 u1 plus n2 u2 plus n3 u3. Likewise, we have to consider. Okay. So what we are supposed to do is, okay, substitute n1, n2, and n3 multiplied by u1, u2, and u3. So for that, we need to find u1, u2, u3. If you want to find u1, u2, u3, you're supposed to substitute here the generic form u1, u2, u3. We will ask already mentioned here, isn't it? u1, u2, u3 is be equal to, what is the generic form here? u1, u2, u3 must be equal to a0, a1, a2, a1, x1, y1, 1, x2, y2, 1, here x3 and y3. So here in this equation, we also substitute the value of A0, A1, and A2. What is the value of A0, A1, and A2 here? So this entire value. This entire value. Right. To substitute this entire value here, this value 1 by 2a into alpha 1 alpha 2 alpha 3 is okay. So these things you have to substitute. Otherwise, first of all, we need to know what is U1 here. Okay. U1 is nothing but this into this plus this into this plus this into this. A0 plus A1 into X1 plus A2 into Y. So what is its value here? A0 is equal to what? So it is 1 by 2a alpha 1, alpha 2, and alpha 3. Okay, alpha 1, alpha 2, and alpha 3. What is the generic form here? It is essentially X, isn't it? It's not X1, Y. It's supposed to be X. So we need to consider, we need to convert this into generic form N1 U1 plus N2 U2 plus N3 U3 like this. Okay. So here, if you convert this, you will get simple term you can write. U is equal to, you can write 1 by 2a into alpha 1 plus beta 1 x plus gamma 1 y. So similarly, we'll get alpha 2 plus beta 2 x plus gamma 2 y. Similarly, we'll get alpha 3 plus beta 3 x plus gamma 3 y. Multiply with u1, u2, and u3. Okay. Because you get u is equal to what? Is equal to a0 plus a1x plus a2y. Okay. So here u is equal to what? In terms of matrix, you can write 1xy multiplied by a0, a1, and a2. Okay. If you substitute this a0, a1, a2 value here, this is a0, a1, a2 value, this value, 1 by 2a, and this value. So this is the value. If you substitute this, so here in this equation, instead of a0, a1, a2 value, you will get this equation, alpha 1 plus beta. So in turn, what we can infer from this? What we can infer from this? So we can write the same function. N1 is equal to what? 1 by 2a into alpha 1 plus beta 1x plus gamma 1y. Similarly, what is the N2 value? Is equal to 1 by 2a into alpha 2 plus beta 2x plus gamma 2y. Similarly, M3 must be equal to 1 by 2a into alpha 3 plus beta 3x plus gamma 3y. So this is the shape function for the CST element. So in this so we will see some more problems based on this CST element in the upcoming sessions. Okay.